Thanks, Peter. All right, so this is really first of all, you've heard two keynotes which were radical and crazy ideas. This kind of, I think, is pretty extreme that way. And also, they presented the work of various people. This is probably presenting the work of like 100 or so different people and a huge number of students and administrators from the different universities and companies involved. So this is about Massachusetts Open Cloud, which is a realization of a new model, which we call an open cloud exchange. So we all know clouds are having this huge impact, right? You know, people can come to a cloud, they can get computers when they need them, they can release them when they don't need them, so they're only paying for what they want, and the provider has enormous economies of scale. You can buy thousands of computers and locate it where power is cheap. So that's great. A lot of people think that cloud computing is the future of all computing. And I think that for those economic reasons, it's true. But the question is, you know, are we really going to live in a world where clouds are basically black boxes, where they're stood up by a single provider who controls the whole cloud? And how do researchers get involved in clouds? That's kind of the two fundamental questions. How does broader industry get involved? How does innovation happen in a fast way? And how can research be involved in these efforts? So these black boxes, what's the problem? Well, first of all, you know, there's lots of innovation that's happening above the IIS layer in these clouds. But, you know, if you have companies like Enterprise DB, for example, did this awesome self-scaling database, and after a while it got enough customers, Amazon said, geez, we should put that to the core platform, and sort of drove them out of business. You know, Akamai, you have this great content distribution network, but, you know, if you look at most of the clouds today, they have their own content distribution network. So there's enormous competition between the clouds, the single providers themselves, and the clouds on top of them. There's a lot of different providers out there, but if you talk about it, you know, you could move to one or the other, but getting your information between those clouds is like sipping at the ocean through a straw. If you actually want to move petabytes of data, you know, there's just no way of doing it. You're sort of locked into one cloud or the other. There's no visibility, no auditing of the internal operations of the clouds. The model is trust us. I don't know, that doesn't kind of resonate with me so well. And while a lot of people think the price is compelling, it's terrible. I mean, the price is great if you have highly elastic computing, but, you know, if you're a university, the prices are orders of magnitude more expensive. Well, at least binary orders of magnitude more expensive than our internal operations. And of course, you can't say details because that involves pricing, but it's incredibly expensive if you have infinite amount of demand, which all of us have in academia. So the fundamental problem is the incentives of the providers are not aligned with creating a marketplace. They're aligned with locking you into their cloud, right? That's the fundamental problem we have here. And it's also, you know, aligned with sort of matching particular demands that exist right now, not with things that are maybe niche markets today, but maybe huge markets in the future. When I started thinking about cloud computing, back when Jonathan convinced me this was going to be a huge thing in IBM, you know, I don't know, 15 years ago, it was actually the thought that tremendous innovation could happen here, because you could do something in cloud and the whole world could come and use it. So even if it addresses 1% of the market, well, you know, if the whole world's coming to it, it could be a massive thing. And it's happened the exact opposite almost. It's only addressing the sort of majority part of the market. So what we think is today, while cloud seems to be doing really well, we're really still an equivalent, and this is dating myself, I apologize, but in sort of the pre-internet world, in the world where AOL or CompuServe sort of dominate the market. So we've been sort of struggling to figure out as an alternative possible. Is a model where you have a cloud, and let's sort of start off with one data center, where lots of people can provide infrastructure, can do innovation in new kinds of architecture or new kinds of infrastructure and expose it in the cloud and actually be remunerated for doing it. Where lots of people and professional IT services and different companies can stand up, you know, cloud services on top of that infrastructure and move and choose between what infrastructure they're going to use and grow and shrink based on demand. Where research groups can actually set up their own services in the middle of a production cloud, you know, getting access to real data and real users as they're doing that. And when you think about that, it sounds incredibly complicated, right? I mean, Amazon is insanely complicated as it is with 48 different types of VMs. But if we're going to have all these different companies exposing their values, and we're creating a marketplace. But if you talk to economists, they say as soon as you create a marketplace, what you get is intermediaries, people that are solving the problems of particular communities of users, and they can actually then use the mechanisms in the marketplace to actually get the better value. So, multiple people can actually stand up those intermediaries in a level playing field. And we think that if that model develops, that has to be inside data centers where you have unbelievable internal bandwidth, but it also has to be replicated across multiple data centers. And eventually, and this is sort of the kicker, I think, it has to go out to cloudlets, to small data centers, tens of machines that are located in individual buildings or individual buses. And this has to be open. There's no way that you're going to have Amazon owning, every cloudlets in every building, right? How do we create a model that extends all the way out to the edge? So this is sort of the vision we've been sort of conjecturing was possible. And what we're really saying is we want to move from, today we have the big box store to kind of a model of a shopping mall where there's many, many specialized shops servicing particular customers. Or as was demonstrated to be very successful, from a cathedral mall to a bazaar model. We know that in our field, every time this has happened, when you broke up the big telephone companies and you had competition, or field after field of technology, that's always resulted in disruption, but then enormous growth and innovation. So we kind of know this is going to happen in some way, fashion, or form. But for us as researchers, this is actually critically important. If the future's in the cloud, and we don't have access to real information, we can't do research. If we can't get access to real data sets and real metadata about what's going on in the cloud, if we don't have access to what users are actually using, or access to scale to be able to do large-scale experiments, and you're not going to get that just by people buying infrastructure for doing research. You're going to get that by multiplexing resources out of a production cloud. If we don't have access to that, we're solving the circular horse problem. Who knows what the circular horse problem is? Okay, so this is the story of, the short part of it is, as physicist says, he can figure out who can win every horse race or what horse will win every horse race. But, a little caveat, the horse has to be circular and running in a vacuum. So, that's what we're doing as researchers if we don't have access to real infrastructure. This isn't insane. Current clouds, as I said, are extremely expensive. Most of industry is locked out of innovation in the clouds. They can't expose their stuff in the real public clouds that exist today. There's lots of great stuff we can do and it doesn't have to hit AWS scale to actually be to get the economies of scale. Past a few thousand machines, you're actually doing pretty good. So we decided to do it. This is a picture of the former governor of the state of Massachusetts, Deval Patrick, and a whole bunch of us getting up on stage to declare the opening of the creation of the Mass Open Cloud. When you work with government, they want to announce things before you actually have any money. So that was about 8 months later, we finally got some initial funding. This is the data center we're doing in it. This is this incredible data center that was built by sort of a small collaboration of a few universities in Massachusetts, so Boston University, Northeastern, MIT, Harvard, and UMass, the whole UMass system. So you're talking about 15 megawatts located right next to a hydro dam, power that's 1/3 the cost of what is in Boston, and 2 acres of room for computers. So that was an incredible opportunity. We had this shared data center that was to be created by the institutions, and a small community of a couple of 100,000 students. Forced customers. So all the 5 universities agreed to participate in this initiative. The state, the U.S. Air Force rapidly got involved and interested in this. We went out and talked to a lot of different companies about getting involved. We have had 5 core partners from the very beginning of the project, so Intel, Lenovo, Brocade, Red Hat, and 2 Sigma. Is Larry here, by the way? Oh, there he is. Good. So at the end of the talk, this is representing a lot of people's work. So Larry over there and Peter here are both people you can talk to about everything going on here. And then sort of a whole bunch of other companies that participate in very smaller ways. These core industry partners really kind of guide us and help make sure that we're sort of addressing the key issues. So this involves a very large ecosystem. So we have the university research IT departments from all 5 institutions, the industry partners. It's got a whole bunch of courses being taught on and in the cloud. We have our first few hundred users that are actually using it, doing all kinds of neat stuff on top of it. Data that's starting to flow in, and I'll talk about that in a second. And then we have a lot of researchers. And the majority of this talk is going to be about some of the different projects, just a sampling of the research projects that are going on that are either necessitated by this model of an open cloud that we're talking about, or that are enabled by this model. And it's been sort of a very small core team. We have about 5 professional engineers that are working on it. And at any given time, I think there's about 30 students, 20 to 30 students that are involved in the development of this. So it's also been a huge educational opportunity. So how do you start this thing? Well, we started off with OpenStack. It sort of was a good basis, despite innumerable challenges, but it had a whole bunch of separate services, each defined with a well-defined API. You could scale each of these, and at least when you kind of squint your eyes, it looks like something that would allow different people to stand up different services in this environment. Turns out that didn't work. After like 4 iterations of working with the community, what we wanted to do was have something where different people could stand up services. Multiple people could stand up storage services. Multiple people could stand up compute services and be provided to customers or intermediaries that acted on top of that. It took us about 3 years to come up with something that the community would accept it. And this was a large team that eventually participated in it from both Red Hat and research groups. But we now have something that's going upstream in OpenStack that will actually allow multiple different groups to actually stand up different services. It's tiny. It's got several hundred users, a couple hundred servers, and it's just basically a OpenStack IIS service today. But there's a huge number of services now being stood up on top of that over the next few months, and it's been this incredible thing of, I don't know how many different research projects are going on or above or enabled by this project. So I'm going to first talk about some of the research challenges. So some of the things we have to solve, some of them which are being addressed by different groups, and some of them which are, actually just still very open problems. And then I'll talk about some of the research enabled. So the first thing is marketplace mechanisms. And, I've been talking to a bunch of people about this, and I don't really know yet what the right answers are going to be, and I think it's going to be very open. But Orran, for example, over there, spent last night talking about all kinds of ideas of how you can expose this. But it's really a different challenge. If you look at it today, you want to have research groups that can buy in with infrastructure into this and be able to use all kinds of different stuff. Universities that can actually participate by their research IT departments doing things and supporting other people and getting credits for doing that. At the same time, you're only going to achieve a scale if you have external customers that are paying money in various models for doing this. So creating a marketplace with different kinds of models and assumptions about what currency people are willing to pay and how you trade off between the resources people can do and what they can get out of it. But it's been a really neat experience as we've gone down this and thinking about how to expand this, because you have groups, for example, that say, I have no reason to participate in this. I 100% use all the capacity that I put in my HPC cluster, for example. And after a little while, you say to them, well, geez, what if you could get 120% at the end of the month, but at certain times you'd only have like 60%. They're like, oh, we're fine with that. That would be awesome. Well, we have other customers of the cloud that actually are interactive that want to get resources when they need it. So it's a very neat thing if we can figure out the right mechanisms to allow for the trading of resources between these communities. Hosting data sets. So when we started, we wanted to start hosting different data sets, and we really looked at Amazon's model. We thought, oh, geez, that's awesome. They host all these public data sets, and a lot of people are actually using these data sets and doing their science on top of it, and that's great. And then we actually met with people that built real data repository systems, and they said, that's just bullshit. A real data repository system provides incentives for people to provide their data, right? Amazon doesn't do that. It provides mechanisms for people to share within a community, a research community. It provides mechanisms, for example, to discover data. So we have folks in the state, for example, that are totally willing and excited to provide their data sets for people to do all kinds of neat analytics on top of it. For example, the MBTA, the bus company, they have data for every minute for the last 30 years where every bus in the state has been. But you know what? there's the name of the bus driver in there. And they don't know what other information is in there. So they want to make it so people can discover their data set, can ask for permission to use it, and then they'll grant permission under some sort of conditions depending on who's asking for it. But they're not even going to put it into the cloud if we tell them you have to clean the data first, you have to fully anonymize it, right? Then all the risk is on them. So the data is never going to move into the cloud. So we started working actually with this group from Harvard. They have this mechanism now where you can actually have a DOI. You can actually cite a data set. So the incentive for a research group is it becomes a citable thing, just like a paper does. And I think in the future, 10 years from now, you're going to see that people are going to have just as many citations and demonstrate value to the academic community through their citations for data sets that they've done as papers that they've actually published. Because that data is going to become essential. So the Dataverse community is pretty cool. They have about 22 installations across the world where different groups have installed the repository control system, geographically where the data, for example, has to live. They have something like 50,000 different data sets in this repository system today. But the model is you have a data depositor that puts their data in, and then users end up copying the data out over the internet. Well, that's great, but how do you deal with terabyte data sets? It's mostly limited to social sciences, to small data sets today. And if you want a complex, that's great if you're going to be just doing simple scripts on it. But if you actually want to have a complex computational environment in order to analyze those data sets, or want reproducibility and want the same kind of computational environment as the data set was originally analyzed on, there's no sort of mechanisms on it. So the teams kind of work together. We now have a new project called Cloud Dataverse, where it persists the data set inside the object store in our cloud. And that means that people can automatically, now all these lines are inside the cloud, people can spin up a computational environment and access the data in situ, in the object store with the cloud, which is a huge advantage. And furthermore, we can actually spin up an on-demand environment, like a Hadoop or a Spark environment, in the click of a button now with the new UI we've worked on the team together. And I think this merger of dataset repository systems and cloud is going to be sort of fundamental to move forward, not just public data sets, but a rich model. So that's one of the challenges I think we've been very successful in starting to address. Multi-provider cloud, we're not even touching that yet, but I think that's going to be huge, is how do we actually, as these cloudlets start moving into buildings, into buses, who's going to control these things? How do we determine the locality of them, where we want that computation to go? Because again, this can't be owned by one provider. Peter's been sort of thinking a lot about, software-defined storage. So if you have a cloud environment and you want to have a diversity of different storage services, you could think about moving the infrastructure, the computational infrastructure fairly rapidly between one compute service and another compute service based on demand. But moving data out of disks is a heck of a lot slower, right? So how do we allow for a diversity of storage services where they can grow or shrink and be stood up by different providers in an environment where we have storage rather than compute? I'm not going to try to answer that question, but you can talk to Peter. HPC, this has become sort of really interesting. So if you look at Amazon today or Google, they actually have spot markets because their infrastructure is underutilized a lot of the time. You never want to turn a customer away if you're charging a consumption-based model. So you end up having more infrastructure than you need most of the time, and you want to actually satisfy that peak. We have infinite high-performance computing demand. So we've been working with some of the compute clusters and production compute clusters at MIT and other groups so that they can warp out and expand and contract to use up all those idle cycles from the interactive uses of the cloud. And that's been changes in the HPC environment. And I think it's also, what's really exciting to me about what we can do here is HPC has always been sort of available for the ivory towers, for Department of Energy, big national labs, for big universities. What happens when this capacity becomes available to anybody who has a technical computing problem? I actually think at the end, high performance and high throughput computing is going to be the dominant workloads in the cloud. So one of the things I've been talking a lot about, moving infrastructure to wherever the usage of that infrastructure is. This project has sort of consumed a lot of our cycles over the time. today in our data center, we have different silos, standing up an HPC cluster, a Hadoop cluster, our OpenStack cluster. And if you actually want to move the resources between them, it turns out to be very expensive. These things, you actually have to have a human being go and manually change the networking in the data center, if not physically move stuff between them. So we ended up looking a lot at all the tools that were out there. And all the tools that were out there sort of coupled a provisioning system with a network isolation system. So we ended up sort of thinking, no, that's not what we want to do. We want to have a very fundamental layer in the data center, if you like an exokernel or microkernel for the data center, where all it does is the network isolation. And that turned out to actually be fairly simple to do. Just a layer where you can allocate for a pod of computers, out of it physical computers, your networks, both your management networks as well as your data networks, and then assign them to a service. And what's been really cool about that is since we allocate the management networks as well, you can assign them to any of the provisioning systems out there. So this has been crucial because the people that have an HPC service can go and use that to use their own provisioning service to then deploy on top of it. So it's been kind of really cool. It means that we can take, for example, our cloud environment, we can go and say, okay, now we want to take all this down. We're being underutilized and actually move that to the HPC environment. We can stand up specialized environments like, a NeuroDebian HPC cluster for a community that needs that. And then when the cloud actually needs its resources, can warp back and get back. Security was actually something that isn't a concern for us, primarily because we were talking about environments that sort of trust each other, that were professionally administered. So we were fine with that at first, and that rapidly became a really stupid decision on our part because we wanted to enable people to do new innovative stuff with the hardware. And as soon as they did that, and you allow a graduate student to do that, if he futzes with a firmware, that's not a great idea. So, and then we started talking to folks from the Air Force, and they had a really interesting challenge because they had all this infrastructure. I'm not going to talk about how bad the utilization is because it's sort of mind-blowing. And at first I thought that was crazy, and then I realized, no, it actually made sense. It's because they have that infrastructure to deal with national emergencies that never happen, right? So you don't want your fire trucks to be 100% used. You want them to be a few percentage used. So that's kind of the same scenario here. So what would happen if we could provide an environment where somebody could have a small, physically secure environment and rapidly warp out and grab the whole environment in the case of a national emergency? And so this has become a joint project with the US Air Force, Lincoln Labs, Lenovo, Intel, and a bunch of scientists from our group to do this. It involves integrating an attestation infrastructure, which rather than providing the attestation to the provider, and then the provider says to the user, trust me, it's secure, right? It provides an attestation to the end tenant, right? So to the Air Force, or to somebody that wants to use the infrastructure of what exactly is put in the firmware at every layer inside this. And a lot of work that we're doing on securing the firmware. And it's got multiple uses. Multiple companies can actually get secure infrastructure out of that same environment. Yeah, I guess that's enough. From a speed perspective, we ended up fairly rapidly realizing that we didn't want to move these images of machines and install them into local disks. Many times you have gigabyte images of Linux environments. And as we started thinking about it, we realized that's kind of silly because you end up, the buffer cache does a pretty good job in operating systems for the boot disk. And even if it didn't, if we're talking about, multiple 10 gig NICs, and a distributed environment and a distributed file system, we felt we could do a pretty good job. And so we built a remote environment where you actually can boot over the network. That's an optional provisioning system. People can use their existing provisioning systems, but if they choose to use that, the cool part about this is they're booting in under 5 minutes compared to 50 minutes for a standard installation. But also we can deprovision a machine, use it for a different purpose, then reprovision it back, or reallocate back to the original use. It just boots from the disk it already had. So it doesn't go through any kind of customization. So this has allowed us to multiplex the infrastructure rapidly. There's just tons more interesting research challenges that come from trying to go after this open cloud model. If you look at our existing clouds, they don't expose, the public clouds out there, they don't expose anything about what's going on in the cloud. So, for example, there's this really cool paper that analyzed the 48 different types of VMs you can have on Amazon, the connectivity to storage, the connectivity between the different class of VMs, how long it took to stand them up. It sort of went through this whole classification. At the end, that paper, trying to analyze which VMs to use for their applications, they spent about $50,000 on the study. And I'm not convinced that that wasn't specific, the results they got to the day they did the study on, right? Trying to extract that information from the outside, I don't think that's the future of optimizing our applications on the cloud. So how do we expose the information without violating customer privacy, especially if users are going to use multiple different providers of infrastructure? How do we correlate between the information of the higher level services and the lower level services that are deployed by different providers? And how do we identify who's actually the source of failure? How do we so you can think about storage sitting somewhere in the data center and multiple storage providers. You can think about compute, and you can think about sort of mixing and matching between the uses. But how do you actually deal with a network marketplace? Networks are going to be essential. A lot of the innovation is happening by different networking providers. So how do we allow that to be a marketplace in our cloud? And again, sort of another person from our community, Rodrigo Fonseca from Brown, started working with us on that. And I'll talk a couple words about this stuff. Again, the network is sort of like the air conditioning of the data center. You don't think about it. So we ended up going down a model where we have multiple different pods. We assume each of those pods is internally homogeneous and isn't highly over-provisioned, that we actually have lots of networking bandwidth within those different pods. And then the idea is we're going to provide a base networking environment that provides commodity simple networking across them. And then there'll be multiple providers, so you can have innovation within the pods and innovation between the pods. And we've now come up with a model where the user can actually request for different flows what kind of networking he wants to use between the pods, and can select which pods he wants to use. So that's talking about at least a first flush, and again, I presented the work of an awful lot of people, of some of the research challenges that people were introduced to when we started saying we want to create an open cloud. There's also a lot of work that this has just enabled. So for example, Martin Herbert at Boston University is looking at models for how to use and expose different accelerators inside the cloud, and particularly FPGAs. So he was working before with the Microsoft team. The work that actually Peter and Larry have been doing on the data lake stuff, this is sort of cool. So we're getting soon a 20 petabyte data lake that's being stood up by the different universities, that we're going to have access to all that, and that's going to be stood up in our data center. And we don't have full bisection bandwidth across our entire environment. So we have these clusters with massive bandwidth internally, and there's relatively good bandwidth, but not full bisection bandwidth inside that data center. And so what we've implemented now is what we call a data center scale delivery, data center data delivery network, D3N, where it's sort of motivated by ideas from content distribution systems, where we cache the data on the access side of any network bottlenecks in the data center. So the top level located next to the nodes that are accessing it is sort of the first cache, and we're using the same kind of techniques you use in the CDN. Anycast to get to a DNS server to find the local entry for the object store. And we've implemented that inside the Radios gateway. Actually, this is kind of a cool story, just so sort of one of the advantages of this model that we've been doing. There was actually this approach being taken inside the Ceph community. People familiar with Ceph object storage? Yeah. So that was an approach that was being taken. Everybody thought this was going to be highly successful. And our industry partner said, that's great, let's actually demonstrate that in the mass open cloud. So we got a whole bunch of cool hardware, SSDs and servers that were attached to the top of each rack. And we got all that infrastructure up and running, and the project failed. The approach of tiering was actually unsuccessful. You have to go and first, there's a variety of technical reasons why the tiering approach didn't work with Ceph. And so, Peter and I were left with all this hardware, which was kind of a fun problem to have. And so we brought together our industry partners and our students, and we started talking about this thing, and we realized we really wanted to implement a caching solution. So we kind of did that, and what's happened is sort of dramatic. It turns out that it's really easy to cache immutable objects. By caching, we have no overhead because it's just, we modified the Rados gateway, which is the thing that was actually servicing these objects. We're able to get dramatic improved performance. In fact, what was neat here is that, we're actually caching the data where we have full bisection bandwidth at the top of each switch. And this is showing the maximum performance of both our SSDs and our servers. So it's the speed of light, and we're able to very easily saturate that. So we're able to sort of achieve the speed of light for this thing as fast as you could go. This is something that we were able to do rapidly, and now it's actually all getting upstreamed into Ceph. So it was sort of, I think, a cool testament of having industry kind of trying to demonstrate something and then solving the problems in a real way with real users. Then when challenges happen, bringing in the research community. This is both resulting in publications as well as in contributions to the upstream community. So when we started proposing this project, there was actually this large group of researchers working on security problems. We ended up proposing the MAX project a little bit after this. That actually was funded to a large extent because this was a real test bed where people could demonstrate their value. We ended up this being a massive project between a whole bunch of the participating universities, led by Ron Kennedy, and this is, I guess, was a frontier grant out of NSF. It has 13 faculty, 11 postdocs, probably more like 50 graduate students that are working on this stuff, the security stuff, and they're exposing their value through the MOC. And it's also been the case that the MOC's problems have been helping direct sort of some of the security solutions that group's been working on. A couple of the projects, this sort of shows the complex interplay, I think, between the teams. So, out of MIT, there was the secure hardware, there was the elastic building block runtime and the UC analysis out of BU. Those motivated us, these projects, to kind of come up with a hardware isolation layer, the bare metal imaging service I talked about before. And then the combination of that and the security stuff gave us a point to addressing that security use case that I was talking about with the Air Force, which is actually tying back into Dataverses now, and how we can, in Dataverse, express the security requirements of different users for these data sets and reflect them back into the storage and the compute that's used to satisfy them. Similarly, inside the guts of our system, we ended up building a monitoring infrastructure to expose all kinds of information up to potential users, which has kind of resulted in new projects up in the security team. Another cool thing enabled by the MOC was a sort of smart cities project led by Azar Bastavros. So you have, you want to collect information. Boston is sort of a mess. I'm sure many of you guys are aware of sort of all the different cities that kind of form part of it. And imagine if we want to send a police car from Newton to Brookline to Boston, 3 different municipalities that do not talk to each other, right? Or if we actually want to find where to park in the city when you're driving in. So the question is, could you actually build an infrastructure, a platform that would enable all these different groups to put their information into a common place? So that project's kind of been really exciting. And in our environment, in open cloud, you can imagine Schneider Electric, which actually controls the traffic lights in Boston, putting their own hardware into that. They're not going to put their hardware into a public cloud place, but they could put it into an environment like an open cloud where they can actually deliver their own hardware, and it could sit right beside these other platforms. There's a ton of work now going on by different research groups. They're actually analyzing the internal information of our cloud. That's just something that's not generally available. So, things that are mining that information, do analytics on top of it to detect that machines have been compromised, for example. Things that are looking at behavior-based authentication. So, whether people are actually putting their information into their GitHub repository, or looking at the historical information. Well, this person's now logging in. Geez, that's kind of interesting. They're logging in from the Ukraine when normally they log in from, Newton. Is there something going on here? Or detecting or other anomaly detection. And then one of the things we're trying to do is pull this information out of all the different networking components and looking at the network traffic analysis. So, sorry, this isn't we, this is different research groups that are actually pulling information out of our cloud. So I guess the last one I talk about is these highly elastic environments. So I think that key to the future of cloud, to solving technical computing problems, is if somebody can solve these problems in a burst, right? That suddenly makes it economical. If I want to use 1,000 computers for a short period of time, economical to use a cloud environment because you're actually paying on a consumption basis. And the idea that I'm paying for hours of a computer or minutes is not going to work for people that want to solve a problem. And let's kind of walk through one. Well, first, this is work by Jonathan Apavu that I've helped a little bit with, but it's been mainly his. And the idea is that new operating system that they've developed, where it's a library OS. So you have a Linux front end, it spins out a whole bunch of these library operating systems that just launch with the application on other bare metal nodes. And we're kind of tying that together with this Hill and BMI stuff. The question is, can we actually make it possible for somebody to grab 1,000 machines for a fraction of a second, where they have the full performance of all those machines? Now, there's a lot of applications that people have been talking about, but one of them that is compelling to us is sort of this fetal MRI problem, where if you do an MRI image of a fetus, you get out something like this. Like, it's kind of a mess, right? So why? Well, the reason is you can't tell the fetus not to move. So it's just impossible to read. Well, people have taken that and done reconstruction and motion correction, and that can take on a high-end server that's available inside a hospital 24 hours to do that. So it's clinically irrelevant. People are doing this kind of stuff for research purposes, but nobody's doing this for actual clinical use cases. Jonathan's students were able to take this and sort of form the core compute on 1,000 servers and get it down to seconds of time. So we're actually looking at trying to get environments. Like, imagine if every MRI in the country, you were actually trying to do this with it. It suddenly becomes clinically relevant to spin up 1,000 computers for a few seconds to solve a problem. And so that's kind of one of the really exciting problems we're trying to work on that's motivated between the combination of hospitals and universities involved in the initiative. Recently, we've had all the industry involvements that have been core partners. Red Hat actually just announced that they're kind of doing a deeper engagement with it. They committed $5 million to research. They're actually committing a lot of engineering time, which is probably a much larger commitment than that $5 million, to create their first research lab at Boston University to work with us on this project. These are sort of the identified core projects, they're anchor projects that they're going to be involved in. One of them is, and I talked about us working on this infrastructure to collect all this different data. And to them, this is really exciting because a lot of these open source, everything is open source technologies, many of which are core parts of their environment. So this will give them the first environment where we're pulling out information from Linux, in OpenShift, OpenStack, and correlating between those different informations in a real production environment. So they want to provide an environment where they can do that and actually then autonomically sort of change what's happening at these different layers or detect problems between them. And right now, every one of these tools has its own separate monitoring infrastructure. And there's no way of pulling this information into a common place where you can do analytics on it. They're working with us to deploy OpenShift, which is their Kubernetes environment, into the cloud and make it available to students from all these different universities. They've committed to investing with us in this data distribution network, and that's actually, they hired all of Peter and my students as interns this summer to upstream that into Ceph. The Hill and Quads work, so Hill is, as I said, that hardware allocation stuff. They have about 1,000 servers internally that they use for performance testing every time they're releasing products. So they do have a reservation system where they actually reserve those machines for different approaches. So we're working to actually see if we can do their reservation system on top of this hardware allocation system And now both it gives them a model to more rapidly move it between the different use cases, but also now you can imagine using this for both research groups and open source companies and open source researchers to allow people to reserve and do deterministic computation, before releasing products or every time you're releasing a new service. They're working with us and other industry partners to get a test bed of all kinds of different accelerators into the MOC that are available to any of the university researchers. So you can warp out and grab a bunch of accelerators for a few hours of experimentations and have absolute bare metal access to these things to do systems research. And then a breadth of stuff in the Dataverse and analytics side. And we're actually motivated and working together on this end-to-end use case of that radiology in the cloud thing, where you can warp out, tie into an OpenShift environment. So we're pulling the data out of the PACS system in the hospital, anonymizing it, putting it into the cloud backend, and grappling a bunch of machines with accelerators to do that analytics. So that's kind of my summary. This is a small-scale cloud today. We're at the point of now we've got production usage, I guess, in the fall. We're now at the point of starting to scale this thing out and service a larger community. We're willing to talk about it finally because we were kind of hiding from users with the fear that too many would dwarf us. So we now have a few hundred users on it. The key driver is this open cloud model, the idea that multiple people can actually innovate and expose their value in the cloud. It's, I think, got the strong potential. In fact, I think it's almost inevitable. I don't think that the future is the model that a single provider controls each of the clouds in our environment. It gives us both enormous research challenges and enormous opportunities to do research. So it's been, if there's any part this has been incredibly successful on, is enabling a broad community of researchers. And it's really important to have access to real data, users, and scale if we want to have any impact in researchers in the future of cloud, which is sort of the future of computing. So, love to have people involved in the project. Like to see this model replicated in other environments. And with that, I'm open for questions. Peter, Larry, do you guys want to come up? No? Okay. Michael.
You said OpenStack was a challenge. You had to go back 3 years and do it again. You were based on OpenStack, or would you be taking something else, or would you build your own code?
I think the decision to use OpenStack was the right one. It's, I think, still the right decision. It's got sort of some fundamentally right architectural decisions. I think it's the best open source infrastructure as a service offering that's out there today. And I think that that's going to be one of the foundational technologies in this. I think, we're going to have containerized environments, we're going to have bare metal environments, and we're going to have virtualized environments existing on this. And there really isn't another game in town right now. Having said that, I've done at VMware, I did vCloud Director. That was a product. It was an awesome product. You could click a button and install it and use it. But it wasn't a platform. We couldn't evolve it and change it. There wasn't a community of people that were doing different aspects to it. OpenStack turned out to be incredibly difficult to operationalize at the time. It's improved dramatically since then. Yep. Go ahead.
I have two questions. First, what I was missing from the challenges in your foils is how do you isolate one user from another user? In this environment, you have so much innovation at every level. So how these effects of innovation and instability that it should necessarily introduce are being taken.
Right.
That's the first question. The second question is, what's the model for a third party, which is not part of this consortium, of this group of users, to get data from this cloud? So what is the practice of this?
So the first question is, how do we isolate different tenants of the cloud? And the answer is we don't. At a fundamental level, that's not our responsibility as the people trying to stand up and create the fundamental model. That's the responsibility of people standing up services. In our own services at the hardware layer, at the hardware isolation layer, we had to let people allocate their own machines, allocate their own networks, and it depends on that infrastructure, what SLA is available with that particular networking technology. So if they're running on their own physical machines and they've got the right networking technology deployed in that pod, then they actually have a lot of isolation all the way up to the external edge of the data center. And from there, we have unbelievable networking to the outside world. So in this environment, in this cloud, there are environments where people get much, much, much stronger isolation than they can on any other cloud. If they happen to be using our OpenStack service, then they're going to be contending with other VMs on the same machines. If they're using our new containerized service, then they're going to be contending with other containers on those machines. And so it really depends on the particular service that they choose to use and what the requirements are. So that's part of what, we're not trying to be, dictating what the isolation mechanism is. And it really depends on what kind of service you want, on what level of isolation you have. For the storage services, it's a very similar thing. You could actually go and use a storage service, which has a number of disks that you've allocated to yourself out of this infrastructure, or you could use our shared self service, the object storage or the block storage, and you'll get the SLA that you request out of that. Does that answer that first question?
Not really, but...
So the fundamental thing, the fundamental question is, today it's not clear on any cloud. We're trying to not say this is what people should have. We're trying to say we want to provide an incentivized system for people providing technology to the cloud to expose what the attributes of that cloud service are, and for users to be able to select it. So I don't think we're at all ready for having SLAs where users will request a particular SLA and will automatically determine what infrastructure can be used to satisfy that. Instead, we're doing a matching of technology where the user can select the technology that they want.
Well, let's say, can you do an innovation in this environment that would bring the whole cloud down? Okay, because I'm doing something extremely crazy and I just want to innovate. Okay, in a real cloud environment, you have an illusion that you are alone. So you are not alone because you have conventions and so on, but at least by design, they're trying to create an infrastructure architecture that prevents a single user from.
So here we provide stronger guarantees that way. So we block people inside networks. They can get physical machines, but they're locked down on the networking that they can use by either VLANs or VXLANs, or we've been talking with Melnox now about there. So we're only deploying inside there. They can only get physical machines in environments where you have networks that can provide strong isolation. So I think we have at least as strong guarantees as any of the public clouds architecturally that you can't break out of your silo. And that's critical. If you look at sort of some of the cloud testbed projects like Chameleon or Cloud Lab, they try to provide those same guarantees, but at the same point, they're saying, well, if somebody breaks out of it, we might not give them access again to the network because they have a trusted community of users. In our case, it's critical because if we don't satisfy real users' needs, we're not going to grow to any scale that will allow for real access. So this idea of coexistence of a test bed and real users requires us to do that architecturally. And I think we're pretty far along that path. So far, at least, thank God, we haven't actually had those front problems. In fact, John Wilkes came to visit us the other day, was really excited about what students are learning and deploying this and stuff like that. And he said to me, the one major thing he said to me that we've really screwed up on, which was sort of surprising, is when we were talking about, I was talking with great pride that we had no significant failures in the user experience in 9 months. He says, "Wait, are you guaranteeing to users that we won't have that?" I said, "No." He says, "Well, then you're really screwing up. You got to bring down the system at least once a week for an hour, because otherwise users will start assuming that you provide that reliable service. And the first time you have a problem, people will be pissed off. If you don't actually bring it down every so often, your users are going to expect that reliability, and you're going to be really screwed the first time it goes down." So in terms of people wanting access to data, it's, as I said, relatively small scale today, but come and talk to us. We have to put together legal agreements, because it's not, privacy preserving that information. There's all kinds of information exposed in that data. Or join the collaboration of groups that are working on the cloud. Any other questions?
sometimes there's conflict between innovation and interoperability. So if we look at your example of the internet, you kind of got stuck with IPv4.
Yep.
IPv6 never really took off because everybody's worried about interoperability.
Yep.
Is that a concern in your system? Do you have any ideas how you can avoid that?
I think it's the wrong concern to be focused on. We have to be focused on security. There's many different services competing for our time and our dollar today, right? I'd love to have in this environment, many different IIS services. Obviously you want to come in, log in with one ID, and have permission to access these different services. We've done sort of a fairly good job of that. And then a lot of the services are accessible, over, IP. So, Dataverse, you can get to your data sets, you can access the object stores, no matter which compute environment you're running on. And I think it's kind of really important to not try to sort of prejudge, Kubernetes is going to be successful, is going to win, or, IIS services or hardware services. I think that having a diversity of different compute services, different interfaces for accessing those, available in an environment where we have massive bandwidth to a variety of different data services is absolutely fine. Everything's logically accessible over the internet, but that internet better be sitting in one data center or bandwidth problems. So I'm not worried about interoperability, as long as people can come in with a single account and use whatever services they want to use. I'm much more worried about how we're going to do the billing models right and the charging models and the currencies. Any questions? Wow. Okay.